we are looking at the shock tube problem, and we have looked at waves in this context. The motion of waves inside a shock tube is particularly important to the driver section, where expansion waves move in decreasing the pressure, while on the right hand side, that is towards the driven section, you have a shock moving in at supersonic speeds, compressing the driven gases to form a slug of gas which moves at speed u2. In between these two, there is a contact discontinuity that separates the driver gas from the driven gas, and we are looking at the right hand side is the moving shock problem, which has been already discussed. We are looking at solving the left hand and then assembling them together. Till now we have discussed the various waves problems, infinitesimal waves, finite waves, and in the finite waves we came to the method of characteristic solutions of the equations, and we said that the way these waves move, these finite waves move, is that they move along lines dx by dt is equal to u plus a and dx by dt equal to u minus a. These are the C plus and the C minus characteristics respectively, and along C plus characteristics there is a constant, it is a Riemann constant J plus, which is u plus 2a by gamma minus 1, and along C minus characteristic there is another Riemann constant J minus, which is u minus 2a by gamma minus 1. And now if we want to solve any wave flow or wave features, flow feature, then we have to see the total of both C plus and C minus characteristic. Towards the end of the class we had discussed that an important behavior is that when you have a region of non-uniform flow between two uniform flows, then the one set of characteristics become straight lines, while the other set remains curved, and this is very much the case for the expansion wave. So you look at this expansion wave. So this is what is t equal to 0, u is 0 here. So this is p4 t4 a4 u4 equal to 0. Similarly this is p1 t1 a1 and u1 equal to 0. The moment the interface ruptures, diaphragm ruptures, you get a shock moving in the driven section, expansion waves moving in the driver section, and you have the contact discontinuity which separates the driver side from the driven side. Shock causes a mass motion which is u2, and across the contact discontinuity you need these two are the same, p3 equal to p2, u3 equal to u2. So velocities are the same. So here region 3 is a uniform region of u3 p3 t3. Okay. Similarly region 4, that is here, is a uniform region which is quiescent, p4 t4 u4 is 0. Now this particular wave which travels first into the region 4 is the head of the expansion wave. So this is the head of the expansion wave, and the wave that travels the last is the tail of the expansion wave. And if you plot now the characteristics for this, starting from this was the initial starting point, t equal to 0. Okay, so you have this. Now this is, you should understand, now we are dealing with, so this is the convention, this is x and t is going right up here. So x is positive going right from the diaphragm station. So this part of the x is negative. Okay. So, these are C minus characteristics. So, this is region 3 uniform flow, region 4 uniform flow. Now, from our previous understanding, you have the C minus characteristics, which are straight lines that you can see over here, they are spread out like a fan, and C plus characteristics are the curves here. So, they become curved the moment they enter the uniform region, they become straight again. So, this is the understanding. Now, we have to put things together. So, we have been doing the things in parts, now we will put it together along with the shock tube problem. So, how do we solve? Along a particular C plus curve. So, this is a C plus curve. Along this curve, this joins U4 region 4 and region 3, J plus is a constant. Okay. So, along this J plus is a constant. So, we use this particular approach. J plus is constant. So, J plus A equal to J plus B equal to C equal to E. So, it is carried along a particular J plus. So, along C, a particular C plus, J plus is U plus 2A by gamma minus 1, this is constant. Now, if you take in region, so you go back to this picture and you take in region 4, U4, A4 is not 0, only U4 is 0. So, you are actually looking at okay, you are looking at this wave U plus U4 plus A4, this is dx by dt equal to U4 plus A4. That means here it travels only with A4. Okay. Similarly, C minus travels with minus A4 or minus 1 by A4. Okay. So, you have U4 is 0 and A4 is there. So, 0 plus 2 A4 by gamma minus 1 is equal to in any at any other point along this, any other point, if you consider any other point, then in general this is U plus 2A by gamma minus 1. So, you can now relate say A and U, how they vary with each other, and you can do that. So, you can take this. So, A4 is gamma minus 1 by 2 U plus A, or you get 1 minus gamma minus 1 by 2 U by A4 is A by A4. Okay. So, you get this equation. Now, A by A4 is nothing but square root of is equal to root of T by T4. Okay, because A is of course A is square root of gamma RT, and we are considering calorically perfect gases. So, you get T by T4 is gamma minus 1 by 2 U by A4 whole square. So, using the J plus characteristics, now we are in a position to relate the flow variables, pressure along the expansion fan, temperature along the, if you know temperature along the expansion fan, T by T4 is known, 1 minus gamma minus 1 by 2 U by A4 whole square. Now, P by P4 is T by T4 whole power gamma by gamma minus 1, because this is an isentropic process. So, that is how you get these relations. P by P4 is 1 minus gamma minus 1 by 2 U by A4 2 gamma by gamma minus 1. Similarly, you get rho by rho 4. So, now we have got the solution of pressures and temperatures in terms of U. Okay. And A4 is a constant here. So, A4 is the initial condition. Now, how do we relate U? So, for that you go to the C minus characteristics. C minus characteristics are dx by dt is U minus A. So, you get x equal to u minus a multiplied by t. If you look at how these characteristics are, these e minus characteristics, they originate from 0. That means they start from x equal to 0, t equal to 0. So while integrating this constant t plus, you should have a constant here, this is 0, only then it satisfies that condition. So you get x is equal to u minus a into multiplied by t. Okay, so from here we can express u in terms of x by t, that is x by t is u minus a, or u is a plus x by t. Okay, and what is a? A is can be related because we just did the relation here where a is equal to a4 minus gamma minus 1 by 2 u. Okay, you can do the substitution here. Okay, so you can do the substitution here. So that's what is done over here, x equal to u minus a. So a is substituted by a4 plus gamma minus 1 by 2 u. Okay, so here you have 1 plus gamma minus 1 by 2 which is gamma plus 1 by 2, and then solve for u. You get u is equal to 2 by gamma plus 1 a4 plus x by t. So now u can be completely represented in terms of the space and time coordinates. So you can look at the evolution of the expansion waves starting from the point 0 when that particular large pressure differential was imposed between the driver section and driven section. So this gives the evolution of pressure, temperature, velocity, where here x and t are the variables that come into picture. Now our core understanding that we want from here is if you are going to use a shock tube for certain applications, then we would like to know what should be the conditions that need to be given so as to achieve a particular shock Mach number. So that is because that is the gas that we are going to use for any of the experiments or any applications. So if I know that a certain shock Mach number has to be produced, ms, then what should be the pressure ratio that I should give across the shock tube. So this is P4 and P1. So how is P4 and P1, or I can write P4 by P1, how is it related to shock Mach number? This is what we need to know. So now we have done the moving shock analysis, we have done the expansion wave analysis, and we know that shock tube consists of all these regions. They are connected by a contact discontinuity with the boundary condition that pressures are the same and velocities are the same across the contact discontinuity. If you put all of them together, then we can get an expression for P4 by P1 in terms of original shock strength or the shock strength that is required, ms. So how do we go about doing that? We need to know what is the mass motion of gas behind the shock, up. Up is equal to u2 is equal to a1 by gamma p2 by p1 minus 1 2 gamma by gamma plus 1 divided by p2 by p1 plus gamma minus 1 by gamma plus 1. This comes from our moving shock analysis that we did in the previous module. So we have taken that result directly. Now from the expansion wave analysis, we know that P by P4 is 1 minus gamma minus 1 by 2 u by a4, whole power 2 gamma by gamma minus 1. This is known. Now if we connect the region 3 and region 4 of the shock tube, if we connect them, then this becomes P3 by P4, and here U becomes U3 by A4, and the relevant gamma here is of the region 4, which is gamma 4. So that is how this particular term comes about. P3 by P4 is equal to 1 minus gamma 4 minus 1 by 2 U3 by A4 and this power. Now what is the boundary condition across the contact surface? Across the contact surface we have P3 equal to P2 and U3 equal to U2. Okay. Now whatever we just now described, UP is actually U2 the same as U3. Okay. So that is what is given. Now from P3 by P4, from this particular expression, from this expression we can solve for U3. What is the velocity U3, which is 2a4 by gamma 4 minus 1, 1 minus P2 by P4 the whole power gamma 4 minus gamma 1 by 2 gamma 4. It is actually P3 by P4, but P2 and P3 are the same, so you can use either P2 or P3. So we can give this to be P2 by P4. So U3 you got from the expansion wave analysis. This comes from expansion wave analysis, while the U2 that you got here, this comes from moving shock analysis. Moving shock analysis. So this is UP or U2, but U2 is equal to U3, so these two parts must be equal. So you put one to be equal to the other, and now you get a relationship where you have P4, P3, P2, P1, A4 and A1. Okay, so you have all this and you have gamma 1 and gamma 4. This has to be sort of algebraically rearranged so that you can write P4 by P1, okay, on left hand side. This can be done, it can be rearranged, and P4 by P1 comes on the left hand side, and right hand side is all functions of P2 by P1, which is the strength of shock. So P2 by P1 is a function of shock Mach number and gamma only. This is gamma 1. Okay, and you have this term 1 minus gamma 4 minus 1 A1 by A4. So this is very important term, A1 by A4, which is the ratio of the speed of sounds in these two parameters. P2 minus P2 by P1 minus 1 divided by, you have 2 gamma 1 plus gamma plus 1 P2 by P1 minus 1. So if you want shock Mach numbers to be very high, then A1 by A4 this term should be quite small, or in this term if it has to be small, then A4 should be larger than A1. A4 should be greater than A1. And this is a guiding principle when we look at shock tube applications as well as experimentation. We always like to keep the driver side the speed of sound higher than the driven side speed of sound, and this is accomplished by many means. You can get higher A4 by using a different gas, a lighter gas, and usually helium is used to get stronger shock waves with the given pressure ratios. You can only achieve certain P4 by P1, which is limited by the kind of pressure vessels that one has so, or you need other kind of approaches, which is heating the driver gas. The heating can be done a priori or it can be done in situ, that is as the experiment is being done. Some kinds of heating are by adiabatically compressing a gas through a piston. Such kind of shock tubes are called free piston shock tubes, or you can even heat up the gas by combusting certain inflammable materials. So you have a combination of a gas and oxygen, and they can burn together and heat up the gas, that is the driver gas. Though those kind of shock tubes are known as combustion driven shock tubes. So these are some ways by which this ratio A1 by A4 can be modified, and hence one can get higher strengths of P2 by P1 for given P4 by P1. Okay. So this gives you so now this is what we want, basically a relationship that tells us if we know the strength of shock that we require for our application, what should be the pressure ratio to be given across the shock tube. So how do we go about now this entire shock tube analysis? So we have to combine all things together now. So if we know ms, we can calculate that shock Mach number. If you know, you can calculate P2 by P1, and from P2 by P1 you can calculate P4 by P1. P4 by P1. If you know P2 by P1, you also can calculate what is the speed of the shock, temperature ratio, density ratio, as well as the U2 or contact surface speed or speed of gas behind it, U2. They P3 by P4, P2 and P1, P2 and P3 are the same. So P3 by P4 is the pressure ratio across the expansion fan. Okay, so along the expansion fan the process is isentropic. So you can derive the expressions for the variation of flow variables across the expansion fan, and local properties are related to x by t by that simple expression. So you know u is a function of x by t. Okay, so that can be used, and we can use that to find T by T4. Once T by T4 is known, you can get pressure ratios and temperature ratios across the expansion fan. So if you look at all the shock tube relations, they can be expressed either in terms of P2 by P1 or in terms of the primary shock Mach number, that is M1, or it is also known as MS, sometimes called as MS. So all the equations can be represented now in terms of P2 by P1 or MS. So this is the pressure ratio, the initial pressure ratio across the shock tube expressed in terms of P2 by P1, and the same thing expressed in terms of ms. So 2 gamma m1 square minus gamma minus 1 by gamma plus 1 multiplied by 1 minus gamma 4 minus 1 by gamma 1 plus 1 a1 by a4 m1 minus 1 by m1 2 gamma 4 by gamma 4 minus 1. So one has to be very careful with what gammas have to be put where, because in general the two sides of the shock tube need not have the same gas, so need not have the same gamma and need not have the same acoustic speeds also. Okay, so one has to be careful when using these equations. So incident shock, the pressure ratio across the incident shock is this is the same result from a normal shock analysis. Similarly, the temperature ratio, this is because you can solve the incident shock by moving along with the shock, and in the frame of the shock the shock equations become stationary, and therefore you can solve them. And another important variable is the mass motion behind the shock. So mass motion behind the shock, as this goes with W, you have U2, which is also termed as UP, and UP can be written in terms of P2 by P1, and UP for a shock tube U2 is also same as U3 and P2 is same as P3. Okay. So, this is the equation for UP by A2. So, the Mach number now M2 is actually U2 by A2. Okay. Now, the other case that we have to consider is there is a possibility that the shock can go all the way to the end of the wall, and there at the end of the wall suddenly abruptly the velocity has to be brought to 0, which is the no penetration condition. It is an end wall. So, there is no penetration inside. So, u has to go to 0 immediately when the shock comes and hits the end wall, and this is accomplished by reflected shock, okay, WR, where U2 is what is coming into the reflected shock and U5 is 0. Okay. So, this is again a moving shock. This moving shock can be analyzed, WR plus U2 will be the relative velocity. Okay. So, and here you will have WR as the relative velocity, and you can do the analysis for this shock, and this was done the previous module, and we take the results directly from the previous module. The reflected shock Mach number can be represented in terms of the incident shock or the primary shock, and also it can be represented in terms of P1 by P2. Okay. And the pressure ratio similarly can be represented in terms of the incident shock. So, here also the incident shock is what plays the role. So, M1, if you know M1, you can get P5 by P1 and T5 by T1. So, to put now, if you look at the entire shock tube, so you got the equations for shock wave, you got the equations for the contact surface. Now, we have the equations for the expansion fans which come here. Okay. So, the velocity in the expansion fan, it varies gradually, that is a function of x by t. Okay. You have to bear in mind that the xt diagram for an expansion fan is like this. This is x is positive, t positive, and the expansion fan appear like this, C minus characteristics. Okay. So, this is the head of the expansion fan goes at a speed 1 minus A4, tail of the expansion fan goes at a speed 1 by U3 minus A3 is the slope, or it goes at U3 minus A3. This is the tail of the expansion fan. Okay. So, and you can relate A4 and A with respect to U. So, once U is known, all these variables, pressure, temperature, density, can be recovered. So, now let us put all things together. Now, we have solved the entire shock tube problem, and let us see how things go if we look at the shock tube. So, this is a plot of P4 by P1, P5 by P1 and T5 by T1 in terms of shock Mach number. This is what is desired. So, we need if we need a certain P5 by P1 or T5 by T1, then what should be the shock Mach number that needs to be given, and correspondingly what should be the pressure ratio across the shock tube that needs to be given. So, if you do find and calculate that, you can see that the scale is in log. That is because these values really take off exponentially, very quickly they rise. So, if you see the Mach number has just risen from, of course, the shock is always supersonic. So, starting from just beyond Mach 1, even when you reach values of say Mach 3, the kind of pressure ratio that you have to provide to achieve a shock Mach number is almost of the value of around, so it is it's Mach 3 and it is around say 500 to 600 bar or 600 times. So it is quite huge pressure ratio that you have to provide in order to give a certain shock strength. Of course, this is drawn for air with driver and driven as air, but you can always in actual shock tubes when people use it for experimentation, they use lot of methods like either heating or using free piston or combustion, or using very easily you can do it by using helium as a driver. And one more aspect to shock tubes is that you get significant increase of temperature with pressure. If you take the same pressure ratio and you consider a compressor, which is more or less it functions very close to an isentropic process compared to a shock tube, because a shock produces large increase in entropy. So efficiency wise the shock tube is not a very efficient device because it produces lot of entropy in the shock, but if you want to very quickly produce high pressures and high temperatures, then shock tube is a good device. So it has an very effective in producing very high pressures and high temperatures. For the same pressure ratio, if you look at the temperature ratio produced by an isentropic compression, the temperature ratio will be less. This is particularly useful for certain aerodynamic testing at very high enthalpies and high Mach numbers typical to hypersonic flows. So that is where this is quite useful. So let us look at how the all the parameters change during the shock. So I will pause here for a while and look at the analytical solutions, exact solutions that we have, and as the shock propagates how these variables pressure, density, temperature and velocity change. Of course this includes a small portion where there is a reflection of the shock also. Okay, so in time as it goes you can observe the shock is moving, you have the contact discontinuity here and then the reflected shock. This is the primary shock, this is contact discontinuity and reflected shock, and you should also observe that the expansion fans are very gradual. So they gradually change the pressure and temperature. Okay, so with this we have looked at the shock tube problem in great detail. It is a template problem for unsteady gas dynamic flow. Several concepts that are important here: moving shock, reflected shock, the boundary conditions across a contact discontinuity, then the analysis of isentropic waves like the expansion wave, and you could also get isentropic compression waves in particular problems. For example, in the initial portion of having a piston moving in a long tube, if you have a piston moving in a long tube and initially when this is gradually accelerated, then the piston actually compresses the gas in front of it. So later if this is accelerated to higher and higher speeds, then these compression waves catch up and later on form a shock, which was the piston analogy that we discussed during the formation of shock waves. But in the initial time the compression waves, how do they move, can be solved using the finite waves that we had have discussed just now. Now, these are isentropic compression waves similar to the expansion waves, but you should understand that these compression waves, if you have the forcing for quite longer time, then they can actually coalesce together and form shock waves. So, that is where you get this velocity of the piston up to create a certain shock with Mach number ms. Okay. So, if the piston is suddenly accelerated, then it will create a shock wave quite quickly. So, these are also some important situations where you can look at these unsteady problems, and we will solve a few problems, shock tube problem and something on the unsteady nature in the next class.